thing that we talked about at the very start of this section is that a power series is basically a generalization of a polynomial where you have infinitely many terms instead of finitely many terms. And so to continue on thinking about that, we're going to think about, well, how do we do differentiation and integration? Well, if we want to differentiate a polynomial, like x to the fourth minus 3x squared, we would take the derivative of each of those terms separately. We'd take the derivative of x to the fourth as 4x cubed, the derivative of 3x squared would be 6x, and so we'd have 4x cubed minus 6x would be the derivative of our polynomial. We just take the derivative of each term separately, and we combine everything together. And guess what? We can treat power series as like infinitely long polynomials if we want to do either differentiation or integration. This theorem right here, theorem 2, says that we can differentiate and integrate power series term by term. So what does this say here? Assume that our power series, here's just a generic power series, a sub n times x minus c to the n. So c is the center here. Suppose that it has radius convergence, r is bigger than or equal to 0, strictly bigger than 0. Then f is differentiable on that interval, on the interval of the original interval of convergence, or at least from c minus r to c plus r. And we can differentiate and integrate term by term. So if we want to take the derivative of this, here is the derivative, and this might look complicated, but it really, let's look at the derivative one right now. It really is just taking derivatives term by term. So so we have a constant times x minus c to the n. So how do we take the derivative of this? We bring down the exponent, and we subtract 1 from the exponent, so that would make n minus 1. The chain rule says we have to multiply by the derivative of the inside, but the derivative of the inside is just 1. So what's going on here? Bring down the n, subtract 1 from the exponent. That's exactly what we have here. So it's exactly, this formula might look complicated, but it's exactly what we should expect and what we should want. I'll point out one other thing. Note that here we're indexing starting at 0. Here we're indexing starting at 1. Well, why is that? This would be just as valid if we index starting at 0 instead of 1. But the point here is that when n is equal to 0, we just have a sub 0 times 1. So that's just a sub 0, a constant. And so when we take the derivative of the constant, we get 0. So we can just drop that initial term. Not only can we differentiate, but we can also integrate term by term. So when we're integrating each of these, the integral of a sub n times x minus c to the n would be, we increase the exponent here by 1, so n would become n plus 1, but then we'd have to divide by n plus 1. So the integral of a sub n times x minus c to the n is exactly a sub n divided by n plus 1 times x minus c to the n plus 1 power. We're still summing n from 0 to infinity. And this is an indefinite integral. So I'm just sticking here a constant. We usually use c. We're using c in other places, so I'm using a here to help distinguish that. So we can integrate and we can differentiate term by term, and in both of these cases, the radius of convergence is still equal to r. It still is exactly the same thing as it was before. Let's do an example of this just to see how this plays out in practice. Let's find a power series expansion for 1 over 1 minus x quantity squared. So how do we do this? Well, the thing to realize is that 1 over 1 minus x squared is the derivative of 1 over 1 minus x. Right? Because when we apply the quotient rule, we square that and everything, I mean, if you crunch stuff out, you'll see that this all checks out. Well, what is the power series for 1 over 1 minus x? Well, that is n from 0 to infinity of x to the n. This is our standard, our simplest geometric series is going to be 1 plus x squared plus x cubed plus x to the 4th. And we should note when we're writing down our power series expansion, we should be noting what the radius and interval of convergence is. So our power series expansion is valid for absolute value x is less than 1. So let's take the derivative of 1 plus x squared plus x cubed plus x to the 4th. And so that's going to be 0 plus 1 plus 2x plus 3x squared plus 4x cubed plus ... If we want to write this in summation notation, so we change the n from 0 to n is equal to 1, and we bring down the exponent, and we subtract 1 for it. So when n is 1, we get 1 times x to the 0. When n is 2, we get 2 times x to the 1. When n is 3, we get 3 times x squared. So this is exactly what we have, and this is still valid for absolute value x is less than 1. So we'll do at least one more example of this. We'll play around with this, but this is how. So this gives us another powerful reason to care about power series.